All right, we're back. We're still on page 4 of notes 15, and we're now going to do a problem. So we've been talking about how we can write these Riemann sums, sort of generalize them, and then ultimately we want to take a limit. So let's see if we can do it. So we're going to do the integral from 2 to 6. So the 2 and the 6 are super important. Integral from 2 to 6 of, this is our function, so that's f of x. All right, so we need to first find the base. So delta x is, we're going from 2 to 6. We're going to make n equal slices. So it's going to be 6 minus 2 divided by n, or just 4 over n. We need to find the evaluation point. So when you think about your evaluation points, think right Riemann sum, right? So you're where you start, which is 2, and you're going to add delta x, and that'll give you your first point, then add delta x again, then again, then again. So x sub I is going to be where we start, which is 2 plus I times delta x, which in this case is 2 plus 4i over n. All right, so the area of any one rectangle that we're dealing with, and you could draw one. The last one is maybe the best one to draw because I hate drawing rectangles. Can I draw like a rectangle? Ooh, look at that. That's pretty nice. Okay, so the area of one rectangle is going to be delta x, and then the height is f of x sub I. So f of x sub I, delta x, and then we know that f of x is x squared minus 3x plus 2. So let's do it. So write a summation that represents the total area of n rectangles, expand the summation into a clear-cut recognizable function of n, the number of rectangles. All right. I write the problems and I hate the way they sound when I read them, but you know, gotta do what you're gonna do. So f of x is x squared, what is it? Minus 2x, minus 3x plus 2. And then x sub I is 2 plus 4i over n. All right, so we're doing the sum from I equals 1 to n of, so it's f of x sub I. So that's gonna be the quantity 2 plus 4i over n squared minus 3, the quantity 2 plus 4i over n, and then plus 2, and then delta x times 4 over n. Okay, so that, you know, that it always looks ugly at this point. So if you want, you can kind of like, well, I don't know about, I can highlight it. So I'm going to highlight all my x of i's, and then you can see the function is like x squared minus 3x plus 2. And then this is delta x. And so I think we're in good shape. So we need to expand this, and then we're going to expand it and use our things. Spacing on this problem might be questionable. So let's expand. So we got the sum. I'm going to take 4 over n out right away. From 1 to n. All right, so square it, multiply them together is 8 times 2 is 16i over n. Square it, 16i squared over n squared, minus 6, minus 12i over n, and then plus 2. So looking to clean this up, we got a 4, a minus 6, and a plus 2. So that's good. Those are just gone. And then we have a 16i and a minus 12i. So it's not really terrible because a lot of stuff goes away. So let's see, that's going to give us 16, so 4i over n, and then plus 16i squared over n squared. So far, so good, maybe. So I'm going to make this 16 over n squared, because I took out, so I'm taking out this 4 over n and multiplying it by this 4 over n, so that's where that came from, the sum from 1 to n of I. And then I'm going to take out the 16 over n squared, and there's still this, so that'll be plus 64 over n cubed from 1 to n of I squared. Okay, let's use our formulas now. So 16 over n squared, and then the sum of I is n plus 1 over 2. and then plus, and maybe I'll highlight to, I don't know if, I don't really get any feedback on these, like, and any feedback that I get will be like months or years in advance, in the future. They'll be, I don't know. It's useless. The time frame is useless is what I'm saying. So I don't know if highlighting is doing any good, if it's not doing any good. I think it would help me a little if I were trying to like follow along. So this became this, and then this. I have so many colors, but there's only a couple that I like using. And this. Okay. So that's like A of n. So if n is equal to 2, this will tell me what the approximation is using 2 right rectangles. If n is equal to 50, if I plug 50 in everywhere I see an n, it'll give me the approximation with 50. If I plug in 100, etc. So that's A of n. And now what I want to do is I want to take the limit as the number of rectangles approaches infinity. So I'm going to say I want the limit. I'm actually going to copy and paste that. The limit as n approaches infinity. So this is going to be the integral from 2 to 4 of x squared minus 3x plus 2 dx is equal to the limit as n approaches infinity of this thing that I'm going to copy and paste. Of this. So this should all be in parentheses because you want the limit to distribute, and it doesn't like obviously distribute, even though I think almost everybody would do it right. Technically, if those parentheses aren't there, the limit only goes with the first product. It doesn't like distribute over the addition. So you should really have them there. So now, all right, now this is an open question. It depends on the class you're in, depends on the teacher, whatever. How much work you have to show here? I mean, this is essentially 16n squared divided by essentially 2n squared, and that should just give you 8. So I'm going to just do that. And then here, this is really 64 times 2n cubed. So that's really, I'm going to keep it 64 times 2n cubed over 6n cubed. So that's like 64 over 3. So I'm actually just going to write plus 64 over 3. So I'm using the fact that they're polynomials of equal degree, which is also, I mentioned maybe in a previous video, that I get sort of excited when I see like, an n squared in the denominator and the sum of I, because I know that the degree of the denominator and numerator will be the same. And we kind of need that to happen. If the degree of the numerator is bigger than the denominator, then something's gone wrong somewhere. Like if this had been 16 over n instead of n squared, and we had this, like I did something wrong. And you go back and you kind of find it. So I don't know how much work you need to show. Also, I think I crashed this. Yeah, that's supposed to fade. Oh, it is fading. What do you do? Okay, did I not? I don't know. We might be back in business, maybe. So this is 2488 over 3. So I think that this integral right here is equal to 88 over 3 because I think that's the limit of the Riemann sum that we set up. Let's use a calculator and see if that's what it is. So the calculator can do like every step of this, which is a pretty good deal. For some reason the like, so on the thing I'm using to record these, like halfway through the video now, it stopped showing that the mic is working and it drives me insane because like, I don't know if the mic is working and I really, if it's not, like, I don't want to have to go back and like re-record. So we're going we're not going 2 to 4. We're going 2 to 6. 2 to 6. I gotta fix that in the notes. 2 to 6 of I'm hitting the caps lock over and over accidentally. X squared minus 3x plus 2x. 88 over 3, which is exactly what we got. So that's pretty nice. Also, your calculator can do like every step of this basically. So if we say f of x is this, and then we do the sum from I equals 1 to n of f of x sub I is 2 plus 4i over n times delta x, which is 4 over n. We can do this, then we can take the limit. So this is, you want to understand how to do these things because look at what's happening here. It's like doing all the work. You get 88 over 3. So calculator's super good at these. We need to get that good. That's like our goal. So I'm gonna go back here. I have to change the one upper bound. And then, well, if I can get back, or debatable. Oh, maybe, here we go. Okay, so this is not correct. This is supposed to be, that's supposed to be 6. And then I'll highlight it again. So we got it right, but I wrote the wrong integral the second time. All right, that's a really good example. I'm gonna cut the video here. I'll be back in the next one to do the next page. So I will see you there.